Hey everybody, this is Larry. This is day 19th of the April Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Combination sum 4. So I usually solve these live, so it's a bit slow or whatever. Just fast forward or skip ahead or whatever you need to do, 2x. Okay. So you're given a distinct integer. You're given nums and your target and return the number possible. Okay. And target is less than 1,000. That's the key one. So this is going to be regular knapsack. And there are a couple of ways to do it. It's kind of interesting because way back in the day, you would, this was a little bit trickier to write because they're on hash tables and stuff like that. But for this should be pretty okay. It's just basically okay. You have to figure out how to ask this question in a recursive way, and basically the question we're going to ask for dynamic programming for memorization is something like this. So you have a function. Let's just call it what's the screen called again? Count. Okay, let's just call it count. Let's just say we have an index and a current target, right? And then this is basically how many ways are there to get to target? Is it exactly or exactly to target with the suffix away from nums from index to the end, right? And that's basically it. And you can now represent that in terms of in terms of just I just want to see if there's any way to do 0. So there's no 0, but yeah, now you just have to figure out how to answer that. And some of that's going to be just handling the base cases. So n is equal to the number of numbers. So then now if target is equal to maybe I need to, let's call it current target. If current target is equal to 0, maybe that's cleaner actually. If target is equal to 0, return 1, right? That means that there's one way to get to the target. And then now, otherwise, if index is equal to n, then we return 0 because that means that we used up all the numbers. So that the number of ways is 0. So otherwise, so the number of ways that's set that to 0, and then now we're given nums of index, and we can have two decisions to make. One is to use this. So we count the number of ways of using this. So index plus 1 because we just consumed this, and then target minus this. Or the number of ways to not use this, which is just this, right? That's basically roughly the answer. Oh yeah, I was gonna say, what about overflows and modding and stuff like that? So it apparently is guaranteed to fit within a 32-bit int, so we don't have to worry about it. But yeah, there are definitely things we have to handle as well. I think one more edge case is you can either have an if statement here, or you just make that your base case, which is if target is less than 0, we return 0. This depends on a little bit on how you memorize as well, which we'll do in a little bit. But yeah, but that's pretty much it. And then now at the very end, or at the beginning maybe, you just count from the first index, and then the target is just the target. Right now it's going to take exponential time, but let's just see if it is correct. Ooh, that's a little bit spicy and not correct. Why did I write 7? Oh no, why did I write 1? Okay, so 7 is the right answer. 1 is okay. So maybe we're just miscounting a little bit. Oh, I misunderstood this one actually. Sorry, my bad. Which is that you can reuse the same numbers multiple times. So then now we actually just make a small modification. So I misread this a little bit, but you basically just now, okay. The question is, so here, what we said before, and it's a small, easy modification, but I just want to explain it. That's why I'm going a little bit slow. But basically, what we were saying before is, okay, we finished num sub index by not using it. Okay, so we finished num sub index by using it. So that's basically the two, that's why we have this here and this here. But then now, by using it, we actually don't finish it, right? So we actually can just make this modification by just saying we use num sub index, but we can do it again in the future. So then now the simple change is just making this change from index +1 to index, because now you have different transitions, because now you can use it, right? Oh, that's still a little bit wrong. Did I miss something silly? Ow. Man, I really should have read this problem a little bit better, because the number of combinations that add up to target is a little bit vague, I suppose. But yeah, but it turns out that in this one, actually the ordering doesn't matter as well. That makes it a little bit annoying. There's definitely ways to do, but I'm trying to think whether. Yeah, okay. So I did it wrong again. But maybe in doing it wrong, you get to see me doing it in 3 different ways. So now, because before what I thought was that the ordering, if the ordering doesn't matter, meaning that these two are the same, if you say that they're the same, then you might as well keep it in one ordering, and the canonical ordering of it is, you almost seem like you're denormalizing it, and the way to, normalizing it. And if you're normalizing it, then you would normalize it to a monotonically strictly increasing sequence. And if you do it that way, that's basically what my code is doing, because now you use num's index, right? But now your recurrence is a little different. You're saying, okay, actually every step of the way you can use any number, right? And because of that, we would have to change the code a little bit. So now, instead of doing this thing, where we asked the wrong question, because I skipped ahead a little bit. So how many ways are there to get to target? I think that's the new question that we should ask. And now, because of that, there's no ordering on index, so then we can just remove it. These two should still be true. Yeah, we don't need that anymore. And then now let's just start over, and then we just return target. And then here you can say, okay, for x in nums, so for every number we ask ourselves, okay, what happens when we use this number, right? And that's pretty much it. So I solved this problem like 3 different times. Hopefully this makes sense. Yeah, but basically this is saying, what happens if the first number is x, right? And of course, if we go less than 0, we return 0. Otherwise, we just, count the number of ways. And this should be good enough, except for that it runs exponentially. We can probably, I think even the smallest number should time out. Let's see if this times out. If it doesn't, it's still, the answer is just too big. So maybe, I'm too lazy to come up with an actual case, but rest assured that you probably couldn't do something like that, like 1, 2, 4, 8, 16, 32, 64, 128, something like that, right? And then just say, I don't know. Oh, it has to be under 1,000, right? And I guess this is too big. I don't know. I don't know if this is too slow, but okay, so it's too big anyway. Okay, so that aside, because of the 32 thing, this is looking at this, there is probably and definitely a case that it's going to be too slow, because it does run exponentially. So the way that you would solve this is by just introducing memorization. And memorization, of course, is pretty straightforward in this case. Maybe. Yeah. So then now we just have to add caching. The thing to notice is that for this question, it always will give you the same answer, giving the same numbers away, right? So then what you want to do is you want to memorize this function, because for every input we get the same output. So now we know that, and this right now costs O of n every time you call it, not to mention more stuff recursively. So then now what we want to do is just, target can go from 0 to target input, which is up to 1,000, I think. Yeah. Right. So then now we can just go, okay, let's just have to, let's just keep track of it then. So cache is equal to, let's just hit the answer times target plus 1, so that we can, and has cache is equal to force times target plus 1. And then now we have a much simpler problem. We go if has cache of target, we return cache of target, right? And then at the very end we just have to remember to cache it. So we has cache of target is equal to true, and then cache of target is equal to raise, and that's pretty much it. Oh, did I not? Oh, whoops, typo. Pay to win. Yeah. So what is the complexity here? Well, let's give it a submit first, and we'll go over the follow-up. Yeah. So what is the complexity here, right? The time is going to be on the order of target, because like we said, the target is the number of inputs here, and each of these will take O of n times. So this is going to be O of, so time is equal to number of inputs times the time each input uses, right? So that's total time. In case, I always try to make this explicit for dynamic programming, but sometimes I don't. So then now, the question is, yeah. So the number of inputs is equal to O of target, and each input takes O of n. So total time is equal to O of target times n. And as you can kind of guess, what I'm going to say next, maybe if you're a frequent viewer of the show, target is it's an input that is given to you as a constraint, and it does not depend directly on n, and thus it is I mean, there are other definitions, but this is a pseudo polynomial solution for this problem. And in terms of space, you can, this is just O of target. I think this one maybe hopefully is easier to see because we just have 2 arrays to cache the answer. And maybe you can also say maybe recursive stack as well if you want to play around with that, explaining that. But yeah. Yeah, that's pretty much all I have. Let's see. Yeah, I solved this problem. I solved 3 different problems in this one video. Hopefully, I mean, maybe I didn't do it explicitly, but hopefully, seeing the difference and why they are a little different, kind of, let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. Stay good, stay healthy, and to good mental health. And I will see you tomorrow. Let me know. Bye-bye.